Hey everyone, today we're going to learn about enthalpy, what is it, and how does it apply to chemical reactions that we've been learning about. And yes, it's going to bring back in some of that stoichiometry because that's never going to leave chemistry. It is the pride and joy of it. Now this section is a little long in terms of notes. I'm going to tell you what you should write down and what you don't really need to write down. So a lot of this is just information just to give you. You don't necessarily have to write it down. So pay attention to that when I give those comments. Okay, so introduction. Enthalpy is the internal energy plus the product of pressure and volume of the system. So I would kind of know what enthalpy is. So if you're going to write down anything, yes, I think this is very important to kind of write down just this first line. Enthalpy is represented by the letter H. And here it says internal energy, so represented by the letter E. Pressure is represented by the letter P. And volume is represented by the letter V. Understanding this is useful for discussing heat flow in processes that occur under a constant pressure. So we like to keep things at a constant pressure. Energy, pressure, and volume, one thing to know about them is they're all state functions that we learned about from the last section. Okay. So over here, there's not a lot you need to write down here, so don't worry about this. Is just some more information on that pressure/volume part of the equation, because pressure and volume can do work. So delta E involves both heat added or removed from a system, but also work done by or on the system. Most commonly, the only kind of work produced by chemical or physical changes open to the atmosphere is a mechanical work, and usually we associate this with a change in volume, which is why we include volume as part of this equation. A good example of this is a piston can move up and down to maintain constant pressure, and so therefore it works on the surroundings by lifting the piston against the force of atmospheric pressure. Down here it's bolded, but I wouldn't necessarily need to write it down. It just says the work involved in the expansion or compression of gas is called pressure-volume work because we're changing the volume to change the pressure. So you don't have to write that down. That's just kind of some background information. Okay. So when pressure is constant in a process, the equation is W equals negative P, and then the little triangle means delta V. Remember, this little triangle means change. So if you're going to find delta V is the final minus initial. And pressure is always either a positive number or 0. So down here, I wrote down two things that you guys can write down. It's in bold. When volume expands, your change in volume is going to be positive, and that means that system does work on the surroundings. Typically, work is negative because energy has left the system. When gases are compressed, means the volume is decreasing. The change in volume is negative. The work is positive and means work is done on the system. And that actually helps us derive the equation that we use for enthalpy. So again, remember enthalpy is delta H, and we can get equals delta E plus P delta V. And then we can actually change that to means H equals Q. So change in enthalpy usually equals the heat QP gained at a loss of a constant pressure. So one thing to write down here is delta H sometimes typically equals Q, the heat gained or lost. So if you're going to write down anything, I'm going to start again. If H is positive, we have gained heat. We're endothermic. Heat is entered. If it's negative, the system released heat, and that means it's exothermic. So how do we determine the sign for H? To indicate the sign of enthalpy change and indicate whether each process is endothermic or exothermic. Here, ice cube melts. So if it's melting, in order to melt, it has to absorb energy to get those molecules moving. So if you're absorbing energy, it's endothermic, which means my delta H is positive because I've taken in energy. For the second part, 1 gram of butane, C4H10, is combusted in sufficient oxygens to give combustion of CO2 and H2O. Think about what combustion means, or combusted. It means to catch fire. So that's going to release heat. So that's exothermic. So that means delta H is going to be negative. So there wasn't much to write down in that section. What's most important is what we're going to be doing now. Delta H, delta meaning change, is your final enthalpy minus your initial enthalpy. And usually it can be written as the products minus reactants. And so we call the whole entire thing, instead of delta H, we can say delta H of the reaction, since we're now applying it to products and reactants. So over here it says, example, 2 moles of hydrogen gas burns to form 2 moles of H2O gas at constant pressure. The system releases 483.6 kilojoules of work. So this is a very good example. If you need to write this down, you should, but you don't have to if you understand it. So here with this reaction, with water being formed, it says delta H is negative 483.6 kilojoules. This negative sign right here tells me it's exothermic. I'm releasing heat. Now notice the delta H is reported at the end of a balanced equation, and it doesn't tell you the amounts of chemicals involved. And that is because here, this number applies to a balanced chemical equation. So we like to use coefficients to represent this number. So whenever you have this equation, the coefficients are 2, 1, 2, this number will always be negative 483.6 kilojoules. But if we change this reaction in any way, it's going to change our delta H. And we're going to talk about how it would be changed in different situations. So guidelines to using thermochemical equations. First thing to know is that enthalpy is an extensive property, which means the magnitude is proportional to the amount of reactant that's going to be used. So typically, if you have a reaction for methane plus O2 yields carbon dioxide and water, here the delta H is negative 890 kilojoules. And that kilojoules goes with 1 mole of CH4, 2 moles of O2. However, if we were to increase this to 2 moles of CH4 and 4 moles of O2, and this would be 2 and this would be 4, that means this number right here has to increase to negative 1780 kilojoules. It has to double because I doubled things down here. If I triple it here, it's got to triple up here. Hopefully that makes sense, because you guys can see that when you guys are going to be doing things later on in this chapter. Because if you take negative 890 times 2, negative 1780. The second guideline is the way the reaction happens is important as well. So our original way that we wrote the equation was CH4 reacts with O2, and I have a negative delta H. But if you flip the equation, so here the reactants became products and the products became reactants. If you flip it and now methane is being created, we have to flip our sign as well. Okay. And the last thing to know about thermochemical equations is the enthalpy is going to depend on the state of the reactants and products. Is the reactant a gas or is it a liquid? It's going to depend on what that kilojoules of energy is going to be. If it is like a gas water vapor, it's negative 802. But if it's liquid water, it's negative 890. So we have to take those into consideration, that states of matter do matter. I'm going to bring up these rules again. It would be a good idea to write them down because you will see them again later on. So here's an example. It says how much heat is released when 4.5 grams of methane gas is burned at a constant pressure system. This is where we're going to bring in stoichiometry. And this is what your homework is going to look a lot alike. If you ever have this, it wants how much heat. So that means we want to get to kilojoules, if that makes sense. Over here, the only number that we're really given in the problem is our grams. So we're going to go ahead and start with grams. 4.5 grams of methane, so CH4. If you ever have grams, you always want to try to get to moles. So here, 1 mole of CH4. And the grams and moles, we have to use molar mass. Molar mass is 16.0426 grams of CH4. And now I have it in moles. Well, what is the relationship between moles and heat? Well, the relationship between moles and heat is the number that you're given in the equation. So here, what you're going to do is you're going to look at the equation and look at the number in front to get rid of moles of CH4. So 1 mole CH4, and whenever there's 1 mole of CH4, the energy released is negative 890 kilojoules. So notice here that it says methane gas is burned, and notice in the equation it's being burned, so I keep that as a negative 890. So make sure they don't flip it. So here if I cancel grams, cancel moles, I'm left with kilojoules of CH4, and I can go ahead and solve this equation. So if you go grab your handy dandy calculator, 4.5 divided by 16.0426 times negative 890 tells me if I had 4.5 grams, that the amount of heat released is going to be negative 249.65 kilojoules. So over here we have a little bit more practice. I want you to kind of try this one on your own and let me know how you guys do. Okay, so let's go ahead and try this together. It says hydrogen peroxide can decompose to water and oxygen by the reaction. H2O2, which is hydrogen peroxide, yields water and oxygen. And our delta H is negative 196 kilojoules. And it wants me to calculate heat, so in kilojoules, released by 5 grams of water decomposing. So the first thing to check is H2O2, does it show it decomposing? Yes, it shows it breaking down. So this number is fine. It can stay the same. So let's go ahead and calculate this. We're given 5 grams of H2O2. To cancel grams, I have to put it on the bottom. So 34.0138 grams H2O2 for 1 mole of H2O2. Okay, next, we want to get moles into heat. Well, the only way to do that is use your number and the balanced equation. So if I use the balanced equation, H2O2 has 2 moles. And the number that is associated with that is negative 196 kilojoules. And now I have everything in kilojoules. You can go ahead and plug it into your calculator. 5 divided by 34.0138 times negative 196 divided by 2. And you get about negative 14.41 kilojoules of heat is released in this reaction. And that brings us to our last example. What if we aren't given grams? What do we do? So here I have a practice problem. The value of delta H for the reaction, it below, is negative 482 kilojoules. So it's for the reaction. So that means here, this is equal to negative 482 kilojoules. So delta H. So this number is associated with the reaction. It's asking us to find grams instead, is produced whenever we have an enthalpy change of negative 1,067 kilojoules. So the number we need to start with is the other number, this negative 1,067 kilojoules. And we want to eventually get to grams. So in order to get to grams or switch to anything, our middleman's always moles. So we have to get kilojoules on the bottom and moles on top. So our kilojoules for the reaction is negative 482. And then our moles, we're trying to get to CO2, so I have to look on the balanced equation. There's 2 moles of CO2 for this reaction. And then to get to moles to grams, we use molar mass. So 1 mole of CO2, and then you find the molar mass, 44.009 grams of CO2. Now that I have in grams of CO2, I can go ahead and solve this. So negative 1067 times 2 divided by negative 482 times 44.009 gets me that in order to get a heat release of negative 1067, what I need to do is I need to have 194.84 grams of CO2. So that's the end of the lesson. Let me know if you have any questions. I'll be more than happy to help, and I hope you guys have a good day.